Let a sub 0, a sub 1, a sub 2, and so on be the sequence defined by the explicit formula a sub n equals c times 2 to the n plus d for each integer n greater than or equal to 0, where c and d are real numbers. Show that for any choice of c and d, a sub k equals 3 times a sub k minus 1 minus 2 times a sub k minus 2 for every integer k greater than or equal to 2. Now, we can actually prove this directly without using any sort of mathematical induction, and that's because we don't need P of k to prove P of k plus 1. We can actually just directly prove P of k for all arbitrary values of k greater than or equal to 2. Now, we can actually prove this directly without using any sort of mathematical induction, and that's because we don't need P of k to prove P of k plus 1. We can actually just directly prove P of k for all arbitrary values of k greater than or equal to 2. So for this proof, we're going to let k be an integer with k greater than or equal to 2. Now, the way we're going to prove this equality here is we're going to evaluate both sides separately, starting from the left-hand side. Now, a sub k can be evaluated using this explicit formula, but we can only use this explicit formula if the index is greater than or equal to 0. Luckily, the index k is greater than or equal to 0, so we can apply the explicit formula. According to the explicit formula, a sub k equals c times 2 to the k plus d. That's the left-hand side of this equation. Now we can evaluate the right-hand side of this equation separately and see if we get the same result. 3 times a sub k minus 1 minus 2 times a sub k minus 2. Now, I'd like to use the explicit formula for a sub k minus 1 and a sub k minus 2, but it's important to clarify that we can actually use this explicit formula because we can only use this explicit formula for integers greater than or equal to 0. If we subtract 1 on both sides of this inequality about k, then we get k minus 1 is greater than or equal to 1. And we can subtract 1 on both sides again to get that k minus 2 is greater than or equal to 0. What's important here, though, is that k minus 2 is greater than or equal to 0, and k minus 1 is greater than or equal to 0. It's also greater than or equal to 1, but more importantly, they're both greater than or equal to 0, which means we can apply the explicit formula for both of these a sub k minus 1 and a sub k minus 2. So if we substitute the explicit formula in for both of these a sub k minus 1 and a sub k minus 2, we get this expression. And we can simplify this expression by distributing the 3 and the minus 2 here. Now, after we distribute the 3 and the negative 2, we can absorb this factor of 2 into this power of 2 to increase this exponent by 1. Moreover, if we have 3d minus 2d, then this is just 1d left. And so now we have 3c times 2 to the k minus 1 minus c times 2 to the k minus 1 minus d. Now we can factor out the 2 to the k minus 1 from these two terms here, and then we can simplify the parentheses to just 2c. And then we can reabsorb another factor of 2 here into this power of 2. And I'm also going to bring the c in the front here so that this is just c times 2 to the k, since k minus 1 plus 1 is equal to k, and then minus d. And if you notice, on both sides of this equation, we get the same expression, c times 2 to the k plus d. And therefore, we've proven this equality for every integer k greater than or equal to 2. Thanks, everyone, and I'll see you in the next video.